Good evening, everyone. Trust you are all doing very well and are taking good care of yourselves and your dear ones. Welcome to the fourth season of Scientifically Speaking. This is a public engagement series initiated by Ashoka University that aims to connect high school students and anyone who is keen to learn with interdisciplinary scientists exploring complex problems. My name is Yukti and I'll be your host for today's session. I'm leading the academic communications work here at Ashoka University. Prior to joining Ashoka, I finished my PhD in chemistry from Tata Institute of Fundamental Research, Mumbai. In today's session, we are going to extensively discuss the spectacular images revealed by NASA's space telescope, famously known as the James Webb Space Telescope. This is the largest and most expensive instrument ever flown. It is 100 times more powerful than the 31 years old Hubble's telescope. Webb can see back in time all the way to the let there be light moment, that instant when the cold dark universe ignited into stars. So without much ado, I will quickly introduce our panelists for today's session. We have with us Professor Kandaswamy Subramanian. Professor Subramanian completed his PhD from TIFR Mumbai. He subsequently pursued his postdoctoral research at the University of Cambridge and University of Sussex, UK, before becoming a faculty member at NCRA TIFR and then at Inter-University Center for Astronomy and Astrophysics, famously known as IUCA, which is situated in Pune. Currently, he is a distinguished professor and dean of visitor academic programs at IUCA. His research encompasses a wide spectrum of astrophysics, including cosmic magnetism. He has received the B.M. Birla Science Prize in Physics. He's a fellow of Indian Academy of Sciences and the Indian National Science Academy. Then next we have with us Professor Manoj Purvankara. He is currently a faculty member at the Department of Astronomy and Astrophysics at TIFR Mumbai. Before joining TIFR, Manoj has worked as a research associate at the University of Rochester, New York, and was a postdoctoral fellow at the Academia Sinica Institute for Astronomy and Astrophysics, Taiwan, and at IUCA, Pune. He completed his PhD from Indian Institute of Astrophysics, Bengaluru in 2005. His primary research interests are in the area of star and planet formation. He's trying to understand the early evolution of newborn stars, protostars, and the formation and subsequent evolution of protoplanetary disks, the birthplaces of planetary systems. He has also been working in the area of exoplanet research. Next, we have with us Dr. Jessie Jose. Jessie is the assistant professor at the Indian Institute of Science, Education and Research, Tirupati. Jessie completed her post-graduation from Christ College, Bengaluru. In 2012, she obtained her PhD from Aryabhat Research Institute of Observational Sciences, Nainital. Later, Jessie pursued her postdoctoral research at the Indian Institute of Astrophysics, Bengaluru, and Kavli Institute of Astronomy and Astrophysics, Peking University, situated in Beijing. Her research interests are in the area of observational astrophysics, star and planet formation, high mass star forming regions in the Milky Way, young brown dwarfs, and free floating planetary mass objects in the solar neighborhood. And last but not the least, we have with us Professor Dipankar Bhattacharya. Dipankar is the Sunanda and Santime Basu Chair Professor in Astrophysics, also the head of the physics department at Ashoka University. Prior to joining Ashoka, he was the Dean of Core Academic Programs at IUCA. He received his bachelor's and master's in physics from Jadavpur University and his PhD from Indian Institute of Science, Bengaluru. He carried out his postdoctoral research at the University of Amsterdam and the University of California, Santa Barbara, and was a member of the faculty at the Raman Research Institute, Bengaluru, before moving to IUCA. Dipankar's research interests cover both theoretical astrophysics and observational astronomy, with particular emphasis on high-energy astrophysics, including compact stars, black holes, and cosmic explosions. So without any further delay, we would like to get the discussion started. All right. So we have been hearing that telescopes are referred to as the time machines that allow us to look back into the past. So on that note, my first question is directed to Professor Dipankar. If you could shed light on how far back in time can we see with the James Webb Space Telescope, and how does this compare with the Hubble's limit?
Thank you, Yukti. Yeah, it's a very interesting question. Webb will certainly be able to look further back in time compared to the Hubble. And there are two main reasons for this. Looking further back in time means looking at objects which are more distant from us. That's because light takes more time to travel from the object to us. And so when we receive the light, we see a snapshot of when the light left the object, which is further back in time. Now, an object which is further away will, of course, look smaller, will look dimmer. So the larger size of the mirror of the Webb compared to the Hubble gives us a big advantage in looking at these fainter and smaller objects. So that is the first factor. The second important factor is cosmological redshift. Objects that are further away from us are more redshifted, which means their light shifts more redwards in wavelength. So if you go to objects which are very far away, visible light emitted from that object gets shifted to infrared. And the Webb is equipped to look at deep infrared. And this deep infrared light allows us to see objects which are more redshifted and therefore which are more distant. So putting it all together, Hubble's limit would have been something like about 500 million years after the Big Bang, whereas Webb can in principle see almost to 100 million years after the Big Bang if light emitting stars and galaxies did exist that far back in time.
Sure. Thank you. Thank you. Let's take this question forward, and I would request Professor Subramanian to answer the next question. If you could shed some more light on, like when we speak of the redshift, what exactly is cosmological redshifting, and what would a redshift of 1100 mean?
Right. I mean, thank you, Yukti, for Dipankar has already said something about redshift, and the thing which I would like to add is that our present notion of the universe is that it's expanding. That is, on the larger scale, all spatial scales are all, increasing with time. And this also applies to the wavelength of the light that is emitted by any particular object. So the wavelength of the light, when it's emitted, if it's some value, at a later time, as the universe is expanding, this wavelength is also increasing with time. So you can define a quantity which is the ratio of the observed to the emitted wavelength, which at present time would be 1 because they're the same. But as you go further and further back in the distant universe, because the universe has expanded from that epoch to today, this ratio would be larger than 1. And so this ratio is characterized by something called the redshift. 1 plus the redshift is the ratio of the observed to emitted wavelength. Redshift is 0 for today's objects. Redshift is higher and higher for objects which are emitting back and back in the past. So this is the basic concept of redshift. The other question which you had about what's special about redshift of 1100, it turns out that the universe also started in a very hot stage, usually colloquially referred to as the Big Bang. And this hot plasma was all completely ionized. The constituents of the universe was like a plasma with positive, negative charges all moving around all over the place. And as the universe expands, it also cools. And as it cools, if it cools to sufficient such that the electrons and the protons and the nuclei can get together to form atoms, then the universe transits from a highly ionized state to a neutral state. That roughly happens at the redshift of about 1100, or when the universe was more compact by about factor of 1100 or 1101. I think that will become clearer in your next this thing also, I think.
Yes. So that's actually lead to my next question, which is that the earliest known light observed was at a redshift of 1100. What happened that allowed that light to be emitted, and is it possible to look deeper into the past?
Well, as the figure that you have displayed shows, I mean, it shows a history of the universe from some very early epoch when the temperature was extremely high, and as it expanded and cooled and cooled and cooled. And we already said that the firstly, this hot universe is associated also with radiation, because all the time radiation is being emitted and absorbed, and the radiation will typically have something called the spread of wavelengths or spectrum, called the thermal spectrum, corresponding to the temperature of the universe. As it cooled and atoms formed, then this radiation gets less interacting with the rest of the plasma in the universe, and it can come free stream to us from what is called the last scattering surface, which is analogous to when you see to a distant cloud and you do not see inside the cloud, but you see all the surface, just on the surface of the cloud, because the radiation from behind has got scattered and only what you see is the surface. So similarly, you see this at a redshift of about 1100 or an age of about 380 or here, or 360,000 years after the Big Bang, the radiation which is last scattered free streams to us. And that comes today as something called the cosmic microwave background. So that's the furthest that we can see in electromagnetic waves. Of course, there are other ways in which you could probe the earlier epochs of the universe. One such thing is the neutrino, which is also a well-known particle, which is much more weakly interacting. And so it can come from even further back in the past. Or what is nowadays extremely fashionable, or gravitational waves, which have been recently discovered. If they are produced in the early universe, they can come to us even further back in the past and probe even earlier epochs. I hope that kind of answers your question.
Yes, the analogy seems to be very helpful in understanding the whole concept. So another question for you, Professor Subramanian, is that to what redshift has Webb already seen, and can it go even deeper?
Well, before Webb, I think the highest redshift galaxy was about redshift of about 11. Okay, so which means the ratio of the observed to emitted wavelengths is 12. What is, of course, these early days, and there are lots of papers and preprints which have already appeared on the archive, and the highest claimed redshift roughly is about 17 or 16.7. It's a rough thing because it's determined not by looking at lines whose wavelengths are very well known in the laboratory, but by looking at the general feature of the radiation in different wave bands that Webb has observed. Can it see much more higher redshift? Yes, provided, of course, because we are working in the infrared wavelength, things which were emitted even in the ultraviolet could come from sources which are at even higher redshift and be seen by the Webb in infrared. So it could even be 30, 40, depending upon how bright objects we can see. So I expect that maybe you will discover a redshift 30 galaxy at some stage.
Interesting. So before we discuss why infrared and why not visible, we'll actually discuss about this, something that made the headlines last week, which was, so this question is directed to Professor Dipankar. If you could tell us about that the micrometeorite that had recently hit the Webb telescope. How bad is the damage to the Webb? Because this had made the headlines, and we would like to clear the air before discussing things in further details.
Yeah, so of course it made headlines because there is a bit of a damage and it is not fully recoverable. But before we are alarmed by this, let me just mention that in the environment that Webb operates in, micrometeorite strikes are expected, and Webb is actually built to withstand most of these micrometeorite strikes. The one that you hear about, which hit the segment C3 as shown in this diagram, was one among the 19 different hits which already happened by by now. Only one among these which could not be fully corrected. So it's corrected by these mirror segments. They are actually slightly flexible, and there is a mechanism behind the mirror segment which can change the shape of the mirror. So it's a small dent which could be caused by these micrometeorite strikes can be recovered by changing the shape of the mirror. This one was a slightly larger than expected hit. We don't know how often this is going to happen, but nonetheless, this hit has produced an unrecoverable residual dent of a size which is roughly about 178 nanometers, which is still a very small fraction of the wavelengths that are being used to operate the web. So yes, it could not be fully recovered, but still it makes only a very minor and small change in the image quality. And the tolerance of the image quality is already much larger than that. So therefore, although this has left a permanent imprint, it has not really substantially changed the image quality of the web. And many of the images that we are actually seeing in the released images, some of the data was acquired after this meteorite strike. So this meteorite strike happened in May, and now we are in August, and the image release happened in July. So already you can see that it's really not affected very much. And the engineers are now evaluating the probability of further such strikes. For example, if the telescope passes through the leftover debris of the Halley's comet, then maybe such meteorite strike rates might go up. So if that evaluation seems important, then it will be turned away. The wave will be pointed away from that direction so that the meteorite strikes become less important. So no major worries. That's my main message.
Sure. Thank you. I think that relieves a lot of tension. This takes us to the next question, again directed to you, Professor Dipankar. We will now be discussing the images that NASA released, and starting with the deep image of the cluster SMACS 0723. If you could tell us how long did it take to capture this particular sharpest image of the distant universe so far, and what are these arc-like structures that we see in the picture?
Yeah, so this is the deepest image among the first light images that was released by the web. And this particular image reportedly has a total exposure of about 12.5 hours. Now, to contrast, the Hubble Deep Field, which was the one which showed the most distant galaxies before, was almost a month-long exposure. So this is done over a much shorter time. So if you take a much longer exposure, you'll be able to go deeper with the web. And already in this image, you see farther and more distant galaxies, fainter galaxies, which were not seen before. In addition, there is also spectral data which they have released connected with this image. So simultaneously, you can measure redshift of objects that you choose in the field, and already a redshift of about 10 was seen among those objects for which the spectra were taken. So this is an excellent pointer to the kind of science that web is going to be able to do. And the arcs that was mentioning, like these that you have marked here, these are in fact gravitationally lensed images of galaxies which are much further away behind the cluster. And gravitational lensing, that is light rays bending due to the mass of the cluster, is a fascinating effect which can tell us various things about the cluster itself and also about the galaxies.
Sure, sure. Thank you. On that note, maybe I can ask Professor Subramanian to elaborate a little more on what is meant by gravitational lensing and what can the lensed images tell us?
Yeah, I mean, this is a really interesting object, as Dipankar already described. See, in Einstein's theory of gravity, light rays can get bent because of the gravitational field of an intervening object. And so, if you have a distant source and an intervening galaxy cluster, galaxies, or even stars, they can bend the light rays around themselves just because of their gravity. So this is different from our normal thing, which we think about as light rays getting bent because of our lenses that we use, like in the specs that we are all wearing. And there it's because of the refractive index of the glass. Here it's because of the effect of the gravity itself. So because it's like lensing, and it also will do many different effects that Dipankar was talking about. Firstly, a background source can be seen multiple times because the light ray from that can get bent through both directions or several directions. So you have multiple images of the same source. If you have a galaxy, which is like distributed stuff, the same effect can distort and amplify the galaxy. Because it can distort, that's what leads to these arc-like structures that you see in this image. And it can also amplify, and so you may be able to see a fainter object behind. If there was not a lens in front, not a gravitational lens in front, you would not have seen it. But because of this amplification effect, now you are able to detect it in your telescope. It's very useful because of the fact that it's sensitive to all the mass. What you see in this picture are only galaxies and stars. What you don't see in this picture is the dark matter which is supposed to exist in the universe. But the bending of the light is sensitive to that also. So it's being used to measure the masses of dark matter in the galaxy cluster, and also used to establish that there is much more dark matter than what you can add up in all the individual galaxies mass that you see. So the fact that it also provides you an amplification, a distortion, a way of a kind of natural telescope, which people call a cosmic telescope, all are very useful effects. But basically, it's the lensing effect due to the gravity that's going on here.
That sounds very interesting, because so far it was all about the change in the refractive index leading to bending of light, but now there are more parameters that lead to bending of light. Thank you so much for elaborating on that. On that note, my next question is for Professor Manoj, and if I could request him to share his screen, I'll continue after.
You go ahead with the question.
Sure. So my question is, if you could tell us a little bit about the different instruments that were embedded on the James Webb Space Telescope. Since none of them work with the visible light, how do we see these beautiful images as if they were really captured by the optical camera?
Sure. So you can see my slide. Right?
Yes.
Yeah. So JWST has 4 instruments on board, and it's useful to categorize them based on the wavelength in which they work. So JWST and all its instruments put together work in the infrared wavelengths, as Dipankar and Professor Subramanian has explained to you. And it works in a wavelength range of 0.6 micrometers to 28 micrometers. Now, if you further divide that wavelength range into near infrared wavelength range from 0.6 to 5 microns, 3 of the instruments on board work in this wavelength range, at the shorter wavelength range. And those instruments are near infrared imager and slitless spectrograph, or NIRIS for short, near infrared camera, or NIRCam for short. So NIRCam is the imaging workhorse of JWST. So the image that Dipankar showed a while ago, that's made by NIRCam. And then the spectroscopic instrument called near infrared spectrograph. There is only one instrument on JWST which works at the longer wavelengths, namely the mid-infrared wavelength, which is 5 to 28 micrometers. And it is called the mid-infrared instrument, or MIRI for short. And these instruments do imaging and spectroscopy and various other things. They have different modes of observation, but let me focus primarily on imaging. So these three instruments that I just described can do imaging. The NIRCam instrument, the NIRIS instrument, and MIRI. MIRI at the longer wavelengths, of course. And the image that I show here is an image made by NIRCam. You know, and I'll use this image to answer the second part of the question, which Yukti asked. Basically, since these are all in infrared wavelengths, right? But why are we then able to see this? We see something. We see these galaxies. How is it possible? Well, James Webb didn't see it with our eye, right? I mean, James Webb detected this using a array of detectors called infrared array, which is made of, it's a semiconductor device made of mercury, cadmium, tellurium array, especially the detector on NIRCam. And NIRCam has 10 such detectors, each of which is 2K by 2K. Roughly, it has roughly about 2,000 picture elements by 2,000 picture elements. It's about 36 millimeter in size, each one of them. And there are 10 such detectors, and they can detect infrared light. And once they have done it, for example, this if you can see my cursor, NIRCam works from roughly around 1 micrometers to 5 micrometers, but we don't observe this entire wavelength at one go. We divide them into smaller bands, 1 to 2 micron, 2 to 3 micron, let's say 3 to 4 micron, 4 to 5 micron, and in smaller filters we observe. Then, and these are detected using those detectors that I just described. And then what we do is we color code them. The light detector in between 1 to 2 micron, we give them a blue color. And light detector between 2 and 3 micron, we give them a red color, as is done here. And light detector in between 3 and 4, we are giving them red. So you have blue, green, and red as you go from shorter wavelengths, 1 to 2 micron to 4 to 5 micron. And what you see here is that a composite image of different filters, but we are giving them visual colors just for us to see. So the galaxies that you see are redder are prominently emitting at 4 and 5 microns, whereas galaxies that you are seeing here as bluer or slightly whitish in color are emitting at shorter wavelengths. So that's the idea. So the instruments on board JWST can also observe in what is known as a spectroscopy mode. So this is just like when a prism will split your sunlight into its colors, right, along the wavelength. So it's just that. So for example, NIRSPEC can do spectroscopy of the image that it sees, and it can also pick up. So for example, in this image that we just showed, NIRSPEC can actually pick up individual galaxies and do spectroscopy. It can disperse the light and identify the elements, certain footprints of or fingerprints of certain elements, and then we can. This is how, in fact, we determine the redshift. And finally, it also has a slitless spectroscopy mode. One example of the use of this particular mode is a transmission spectrum of an exoplanet, which we will talk about in a minute. I'll stop here, Yukti, and then we can take the next question.
Sure. Thank you so much. I think this is very helpful. The pictures give a better idea of the different instruments that this comprehensive telescope carries. So on that note, my next question is directed to Professor Jesse. So what are the advantages of using infrared over visible wavelengths? Because a lot has been said about using IR light to see the objects that emitted that light inside a dusty cloud. So why is this important?
Yeah, thanks, Yukti. I hope I'm audible. You all know the radius scattering condition. The amount of scattering is directly proportional to 1 over lambda at 4th power of the wavelength. So longer the wavelength, less scattering. So that answers your question. So when we look through when we look at a dusty cloud, dusty cloud is the region where you have active star formation, active star and planet formation take place. So when you want to image or when you want to see what is happening inside a cloud, you really need to have a longer wavelength observation like infrared wavelength regime, so that you can penetrate or you can look deeply into the cloud. So the image here in the screen exactly explains that this is not a JWST image. Instead, it's a Hubble images. So on the left side is an optical image of a massive molecular cloud in our solar neighborhood. That is called the Eagle Nebula. So you can see the dark features here, and it has lot of color combination you can see there. So this darkness is mainly because the dust present in the molecular cloud. So the dust within them obscures the radiation coming out of the molecular cloud. So anything from the background or within the cloud cannot be seen in optical. But on the right side, the same region is being imaged with the infrared facility of Hubble, and you can see stars which are lying behind the cloud, as well as from the cloud also. Within the cloud itself, you get to see a lot of information, a lot of light is coming. So that's the advantage of having infrared. And other than this thing, for exoplanet studies, there are spectral features of exoplanet atmospheres which lack the infrared wavelength regime when compared to optical or any other wavelength. That's another advantage of having infrared wavelength. And then other than that, more cooler objects like very younger stars or planetary mass objects, they emit more, their flux density is more towards the longer wavelength when compared to optical or short wave. So that's another advantage of having infrared observations. Yeah.
Sure. Thank you, Jessie, for that comprehensive elaboration. My next question to you is, if you could describe what exactly are we seeing in this image of the Southern Ring Nebula? What do these concentric spheres depict?
So this is Southern Ring Nebula. So this is the images of a planetary nebula on the image taken with this near.
Jessie, your voice is breaking. I think it would be better if you could just turn off your camera. It will save some bandwidth and we should be able to hear you clearly.
Yeah. Unfortunately, I have unstable internet connectivity today. Am I audible now?
Yes, you are audible now.
Okay.
Yes.
Okay. Yeah. So I was trying to say on the left side is the image taken by JWST using NearCam facility, and the right side is the MIRI image of this planetary nebula. So planetary nebula faces one of the end phases of low mass stars, like a sun type star. When sun now it's a main sequence star. When it goes towards its end phase, it will go through every sun type star, or similar to sun type star, essentially go through a phase called red giant. It will go through a phase planetary nebula and shed all the outermost shells around the star, and then finally the center core turns out to be a white dwarf. So this is that particular phase, planetary nebula phase, where this ring features around on the left side. Both the images you see ring features, they are not exactly symmetric or a circular morphology, they are asymmetric in shape. And this shows the nebula or the dusty gas shell having ejected out of the
Jessie, your voice is breaking quite a lot.
Oh, okay. I'm sorry.
Yes, please go ahead.
What do I do now? Yeah. Okay. Did you hear me properly till now, or should I repeat?
Just a last couple of statements, if you could talk about.
Oh, okay. On the right side, if you look at the center of the image, there are two stars. So this is essentially a binary system. One of them is gone to the the white dwarf is which ejected a shell that these two are binary system. They are revolving around its center of mass, and the one which is reddish in color, that is a source for this planetary nebula. So this planetary nebula, it's like a it's asymmetric, and you can see multiple shells, right? One is like a further extended, the other one is like something close by. So it shows the historic, it's an episodic ejection. So multiple rounds of nebular ejection have occurred, and that's how you see different shells of different dimensions. So this kind of objects, you can see the history of the star evolution, stellar evolution. That is the advantage, and the spectroscopic information of this planetary nebula will give a lot of spectral information. Like these features are created from the highly ionized atomic species like argon, silicon, nitrogen, sulfur, etc. So you will get to see from the spectral features the elemental composition as well. Yeah,
sure.
That's
also, Jessie, we see these two little stars, the one that you talked about right now. So how do these stars actually affect the nebula?
Yeah, right. It's like this, as I mentioned, it's a binary system. So both of them are revolving around its center of mass, and then it has hot gas around them. So it's like a stirring the gas pot. So when both of them are revolving around, then it will constantly disturb the gas cloud around them, and that's how you get the asymmetric pattern in the shell.
Sure, understood. This brings us to the very first image that was revealed by NASA of the Carina nebula. What do we see in this, and what can studying such a nebula tell us about how the stars are formed? Jessie, over to you. I think we have lost Jessie. Maybe I can get back to her in a short while. Before that, we can talk about another fantastic image that was released by NASA. And I'll request Professor Subramanian to elaborate on what are we seeing in the Stephens quintet here on the screen.
Yeah, thank you, Yukti. I hope we do get back, Jessie.
Yes.
Yeah, this quintet, of course, means 5 galaxies. So there's a group of galaxies, but actually what you see on the leftmost side, that galaxy is not part of this physical group. It's in front. So it's about 40 million light years away from us. And the other galaxies are about 290 million light years away. So the reason that's interesting is that we believe that the universe, the galaxies formed hierarchically. Smallest galaxies form, then groups form, then they merge, galaxies merge together, become bigger galaxies, etc., until we stop the chain with clusters of galaxies that we saw in the other picture. So there's an interacting group of galaxies, with some of which will merge eventually to become one big galaxy. So there are very interesting things which happen when two galaxies come very close to each other. Just like the moon raises tides on the Earth by its gravitational influence, one galaxy raises tides on the other galaxy and vice versa. So firstly, material is being pulled out from the galaxy. You can see these streams of stuff which is coming out of the topmost guy, for example, or even the one below. And these are things which have been tidally stripped from the other galaxy. What also happens when two galaxies come close together is that they introduce perturbations inside each other, perturbations in the density, which are actually like wave-like. They're called density waves. Those can extract angular momentum of the material which is going round and round the center of the galaxy. And that means that the material can then sink in and feed the central regions. In fact, the northernmost galaxy is believed to be what is called an active galaxy. It has a black hole which is, I think, few tens of million times larger than the black hole on the center of our galaxy, and it's being fed by material. And this accreting material is also being seen in what Manoj showed as one of the spectrum that he showed. And it's also what's also being seen is material which is being ejected. And that spectrum is also showing that there is molecular gas and silicates which are being accreted, cold gas which is being accreted, very hot ionized gas which is being ejected, which has very, things like oxygen. The composition of this ejection is also being seen. So this picture has lots of information. It will tell you probably how galaxies evolve when they're interacting in a group, and will also improve our understanding of how structures formed and evolved through the universe evolution.
Sure. Sure, Professor Subramanian, you already talked about these galaxies that are in the closer vicinity to each other. They do affect the angular momentum of the stuff inside each other, but is it like they also affect the star formation in each other?
Oh, yes, I should have mentioned that. Yes, of course, what happens is there is statistical evidence that when galaxies interact with each other, they induce more star formation in themselves. And this also firstly because of the material sinking in and leading to higher density material, which if you perturb can become gravitationally unstable, form clouds, more clouds, which will eventually collapse to form stars. It can also be because these density waves, which I was talking about, increase the random motions of the clouds already existing in the galaxy. So they can collide more frequently. And then this also means that they can induce shocks and they can make material collapse to form more stars. So yes, they do increase the star formation in each other also.
Sure. Thank you so much for elaborating on that. My next question is for Manoj. The next image that we see is a spectrum that is obtained from an exoplanet WASP 96b. What is an exoplanet? If you could talk about it, please feel free to share your screen. And how exactly are we able to look at the atmosphere of a planet that is like over 1100 light years away? And what does this spectrum tells us?
You can see my screen?
Yes, we can.
Yeah, so let me start with describing what exoplanets are. So exoplanets are planets orbiting stars other than the sun. The only thing is until 1992 or so, we knew of only one planetary system, and in 1992, the two exosolar planets were discovered around a dead star, but it soon we found out that they are not that frequent. But it was really in 1995 that the first planet orbiting a sun-like star other than the sun was discovered, and that is shown in this figure here. And I just want to quickly show you how the situation has changed as of today. We now know of more than 5,063 exosolar planets. And let me directly take on the question now. So what has JWST done in its one of the first spectra that JWST released was that from a planet. It's what's called the transmission spectra. So what happens here is that when the planet is going around the star, and the planet is in front of the star, an observer is here. I'm going to say I am the observer, I'm looking at it, or if you are looking at it. So you see the planet has an atmosphere, and the starlight will pass through the atmosphere of the planet, and you will register that spectra. Now you take another spectra when the planet is outside the stellar disk, and you subtract the second one from the first, and you have the fingerprints of the planet, right? So that is exactly what the JWST has done. And this is what the subtracted spectra is. What is shown here is the subtracted spectra, and here you start picking up the features, the spectroscopic features of molecules in the planet's atmosphere. What is shown here is these distinct features that you see here are caused by water, steam, water vapor. So what this is telling you immediately is that the atmosphere of this planet has water in it. Now, this planet is not an Earth-like planet. This planet is a Jupiter-like planet. This is half a Jupiter mass planet. Its mass is half of that of Jupiter, and its radius is roughly slightly more than Jupiter's radius. So what is really interesting is the how good this spectra is. So until now, no other telescopes, including the Hubble Space Telescope, couldn't get spectra with this sort of, such a clean spectra. What this spectra also is telling us is that, see, we have certain theoretical expectations, and we thought the water vapor features should be stronger, but they are not as strong. So that immediately tells you that there are clouds in the atmosphere of these planets that is blocking some of the light. Otherwise, water vapor feature could have been much stronger. I think, Yuki, I'll stop here and we can discuss it later, I think. Yeah.
Sure. So if I can quickly share my screen again and see if Jesse is back, we would like to discuss the Carina nebula picture once again. Jesse, can you hear me?
Yes, I can hear you. Yeah. So this is, as you all understand, this is one of the most beautiful ones among, which I feel among all the images which they release. So on the left side is it's an image, mid-infrared image taken by Spitzer telescope, and what you see is a bubble-like feature, a circular feature overall. The whole image, if you consider as such. So this bubble has been created by massive star. So when I say massive star, it's like a more than 8 or 10 times heavier than Sun type star. So such massive stars have strong UV radiation, ultraviolet radiation, strong, very powerful stellar winds, and also as soon as such stars form in a molecular cloud, they gives out a lot of radiation, stellar wind, and then the immediate neighborhood will be affected by that. So that's what exactly you see as the bubble. So the area around that massive star have been carved out, and more hot radiation in its vicinity. And the periphery, so on the middle image, the middle and the rightmost images are the one of the borders of this bubble created by the massive star. So what is attractive here is the sharp boundary. So you can see one side is bluish on the middle image, the other side is like orangish, and you have a very sharp boundary in between. So that shows the ionization boundary. So this part of the left side part of the cloud, it's a boundary between ionized gas and the molecular gas. So there is a sharp ionization boundary, and that shows the interaction between the strong ionization radiation, which is pushing the cloud further towards the right side, and that's how you see a boundary there. And it has a lot of other information as well, a lot of details you can. So if you zoom into each region, you will see a lot of stars embedded there, especially in the middle. On the right side, if you look at the middle of the image, you can see a group of young stars, like reddish colored stars. These are the young stars, very young stars embedded in the deep molecular cloud. So it also shows that after the massive star formation pushing the cloud, then the second generation stars are formed in the collected material. So the material has been collected to one side, and then second generation stars are forming there. Also, if you zoom into that image, you'll get to see a lot of features like jets and molecular outflows, etc. So this is a collection of a lot of things happening in this region, and the beauty of JWST images, you get to see a lot of information. For example, newly formed stars, jets, outflows, ionization boundary, and all other physical parameters, etc. You can study from this image. Yeah, if they are done.
Sure. Thank you. So my next question is directed to Professor Dipankar. If you could shed some light on what are the new, why really are these images so important for science? If you could just elaborate on that aspect.
Yeah, actually the first release images have been chosen not specifically for the science impact of those particular images, but to demonstrate the exquisite capabilities of the web. The science from the web is going to come in the time that that now will pass. The sharpness of the images, the depth to which observations can be made, the dust penetrating capability, and the ability to acquire spectra all the way to 28 microns, all of these have been demonstrated by these first release images, and these are going to be fascinating tools for astronomy. And that was why these particular images were chosen. More detailed analysis will be done not only of these images, but for all other observations that Webb will take over time. So these images just give us a glimpse of the science that we can expect from the Webb as more and more observations are taken, not just the science impact of these particular images themselves. Although some of the science that these images are already telling us is being discussed already in this discussion by several of us, so I'm not going to repeat those. But I think the main importance is to demonstrate how powerful Webb can be for science.
Sure, thank you. Thank you. On that note, I would like to highlight the fact that we have with us two researchers who are actually working with the Webb. So I would request Professor Manoj to share his own research program with the James Webb Space.
Maybe you could, Jesse can go first. So
Sure.
I think that way it fits better. Yeah.
Sure.
Jesse, do you want to go first?
Yeah, sure. Yeah.
Just give me 1 sec. I'll just share Jesse's.
Yeah, sure.
Yes, Jesse, please start.
Yeah. So the title of my project is Unveiling the Stellar Birth in Cosmologically Common Cradle. That's a very difficult title for you to get. So what I will be, I'm a co-investigator of an accepted proposal. We are 15 other researchers included in this proposal, and we are being given 27.2 hours of observing time with the JWST. And our program is to use the NearCam and MIRI imaging capabilities of JWST, and the observations will be taken in April 2023. So on the right side, what you see is the artistic impression of our own Milky Way. So we know that red star mark represents our location in the Milky Way plane, our sun and solar system. And at the center of the galaxy, we have the supermassive black hole. But other than the supermassive black hole, the central few hundred parsec, so 1 parsec is roughly 3.2 light years. So like the inner 600, 700 light years space is called the central molecular zone. And that central molecular zone is very special. It has a lot of massive molecular cloud, lot of massive clusters, and it's a dynamically very active region. So in many ways, this Staffelman conditions are very unique or completely different when compared to the solar neighborhood. So our program is to look at, you think maybe you can move to the next slide. So this is the mid-infrared view of the central molecular zone. It's a huge area in the sky. So all the massive clouds and important regions, including the Sagittarius A, everything is marked there. So our program is to look at one of the massive molecular cloud towards this region, and that is called the galactic center cloud, EF. So this is the region which we are looking at, and our program is to look at the star formation as such in that region. So far we do not know what kind of star formation or whether it is actively forming stars or not. So we know it's a very massive cloud. It has all signatures or all the characteristics of having a lot of stars already in it. But then we so far are, because of our limited sensitivity of the current existing facilities other than the JWST, nobody knows what kind of stars are there, or we could not reach up to the detecting the stars in them. So JWST is very ideal capability to detect stars in this region down to we are aiming to detect down to 0.1 or 10 times lower luminosity than sun type stars. So such low mass objects we are aiming to observe in this region. And the major science goals which we are planning to address is whether the star formation is environmentally dependent or not. So we know how the star formation in the solar neighborhood or distant galaxies and all, what are the different the star formation rate. star formation efficiency, etc. So we, by studying this region, we will be addressing the main problem whether the star formation is environmentally dependent or not. And then we also like to see the surface density of the region. Does it affect the star formation rate? That is another important problem. And then we also like to look at the initial mass function. So mass function is nothing but the mass distribution of stars in a given environment or given star forming condition. So whether this kind of unique region or a special region has any difference in the form of IMF when compared to solar neighborhood or distant galaxies. So these are some of the science goals which we plan to address, and we will be using the deeper imaging capability and to identify the young stellar objects, the newly formed stars in the sky.
Sure. Thank you, Jessie, for elaborating that bit. Manoj, can I request you to talk about your research program around the web?
Sure, I need to share my screen. Yeah. So Jessie and their team is looking at the slightly large scale questions about star formation, the large scale star formation or the macro physics of star formation. So what the team which I am part of is going for the details. We are zooming into that cloud and trying to so using this exquisite angular, spatial, and spectral resolution of JWST, we are trying to see how stars are formed at a very small spatial, spectral, and angular scale. So the proposal that the work I am part of, which has JWST time, has a title investigating protostellar accretion across mass spectrum. The PI is Tom McGath of University of Toledo, and I am one of the co-investigators. We have about 66 hours on JWST. So Jessie's project, they are imaging that large molecular cloud in the galactic, towards the galactic center. What we are doing is to just do spectroscopy. See, a spectra gives you a lot more information than an image. So, and we also want to study the exquisite details at very close to the star which is being formed. So we will be using as the NIRSPEC and the MIRI instrument, which I have described to you a while ago. And we will be studying 5 protostars, 5 stars that are currently being born, in the process of being born. And we will also study across a mass range from a tenth of a solar mass to 10 solar masses. In fact, one of our target has already been observed on 22nd and 23rd July with NIRSPEC and MIRI. We are able to see the data. Now, so this is the microscopic physics of star formation. The process begins when the molecular cloud core collapses to form a central object, a disk around it, an overlying envelope from which the material is raining down onto the disk. See, the disk forms because of angular momentum conservation, because the material which are far away from the rotational axis cannot collapse directly onto the central object. It has to first, form a flattened structure like this. So, and eventually the envelope dissipates either by raining down onto the disk or by the action of the wind and outflow. And you're left with a central object and a disk around it. And these are called protoplanetary disks. This is where the planetary systems form. See, one of the great success of modern star formation theory has been its prediction that planet formation is a natural byproduct of the star formation process itself. So stars and planets form together. And it is in this disk that planetary systems form. And eventually, planetary systems form and the disk dissipate away, and you have a mature star like our sun and a planetary system around it. And we want to look at this stage, the very early phases, and we want to look at very closely where the material is, falling into the star, and the star is being built. And when it is so during this phase, the young star that is forming drives powerful jets along the bipolar axis, its polar axis. So we want to study the innermost regions where the material is falling in and building the star, and it is driving this jet. So these mass flows is what eventually forms the star and the disk, where the planetary systems form. See, this is one example of such an outflow driven by a young star. So this bipolar jet. See, the dark lane that you see in the middle, that is actually the disk, and the dust in the disk is blocking light. You can't see that. So, and this structure, ball-like structure that you see here, are the disk surface scattering the light. And these jets. So we want to look at this extremely close regions to this object where material is falling in to building up the star, and the material is being ejected, and in all the while, the disk where the planetary systems will form is being assembled. So this is one such disk. I'm just giving you an example. So when you look at this disk, they already form structures, substructures within them. Presumably, planets have already formed, and they are excavating cavities within the disk. So these are some of the things that we want to address in our project. So I'll stop here, Yukti.
Sure. Thank you, Manoj, and wishing you both all the very best with the upcoming projects. We have a lot of audience questions pouring in, so we'll quickly start taking those because we are just 15 minutes away from closing this session. So my first question is for Professor Subramanian, where somebody is asking what is the difference between a redshift and a blue shift, if you could elaborate that.
Yes, I mean, we keep talking about redshift. I mean, in the normal context in which physics students encounter, you have something moving away from you. And for example, that light gets redshifted, or even if it's a sound wave, it gets, you see that the frequency decreases and the wavelength increases. When something is moving towards you, you will see correspondingly blue shift. Why do we talk only about redshifts in the cosmological context? Because no galaxy likes us. They're all moving away from us on a large scale, on the scale of the big scale where you average over lots of inhomogeneities in this expanding universe. It's like the analogy that one can give is that if you're an ant living on a balloon and you blow the balloon up, or each ant is sitting quietly on the balloon, but each ant is seeing other ants moving away from each other. And so you always see this more in an expanding universe redshift. You don't ever see the blue shift. But of course, in a galaxy, you can have things either moving towards you or away from you. For example, in some of those images of the active galaxies, you will see sometimes inside something falling towards you, which may be moving away from you. Something falling from the other side will be blue shifted. So you can see both red shifts and blue shifts. They're pretty small compared to the cosmological. You don't see any evidence for cosmological blue shifts so far. Sorry, too.
Thank you. My next question is about exoplanets. So it will be directed to Manoj. Somebody is asking if could the most promising exoplanets harbor life? Not sure about what is meant by promising, but is it possible that one or more of the exoplanets are habitable?
Yeah, I think we have to be careful about this definition, habitable. So the working definition, which is widely used in the community, is that a habitable planet is where you can have liquid water. The temperature and pressure is just right. So going by that definition, there are several tens of exoplanets that we know now, that we have discovered now, which could satisfy that criterion. But that doesn't mean that so then you cannot extrapolate it to say then that life exists there or not. So what JWST will do in this context is probably from the transmission spectroscopy, it can measure what are known as biomarkers or biosignatures in the atmosphere. And in the infrared wavelengths, these are typically carbon dioxide, methane. These are generally considered as some indicators of something, life or whatever you want to call it. So that is all JWST can do mostly. But the question of whether, one has to be careful about this word habitability, what that means.
Sure. Thank you for pointing that out. My next question is for Dipankar. Somebody is asking, what are the conditions under which a neutron star gets converted to a black hole?
Yeah, so that, of course, is not directly related to what we are discussing today, but it's an interesting question nevertheless. The neutron star has an upper mass limit. If the object is heavier than a certain amount, then the forces that hold up the neutron star, the nuclear forces, so they're not sufficient to hold it up anymore. So if you start with a neutron star and then you make it more massive, then at some point it will become a black hole. So how to make it more massive? So neutron star then has to acquire mass from somewhere. Either from a binary companion star, it can attract mass and mass falls onto it. Or maybe two neutron stars going around each other and then they merge. And then the merged object is heavier than what the neutron star can sustain, and therefore it can become a black hole. So these are various ways where it can happen.
Sure, sure. My next question is for Professor Subramanian. Somebody is asking, how can the elements be identified just by using light? And how does the wavelength of light change in space? Yeah.
I mean, I think the basic thing is if you have no features in the light, then of course you can't do anything. But we know from quantum mechanics, so to speak, or even just that every element or atom or of various kinds emit line radiation of particular frequencies, because the energy occupied by whatever electron, etc., are in discrete energy levels. So when there's a transition from some higher energy state to a lower energy state, it's of a particular energy. And so this leaves like a fingerprint of each element in what you call the spectrum, or the amount of energy coming as a function of frequency or wavelength. Now, in the course of expansion or redshifting or whatever, this spectrum gets shifted to a different wavelength. So, but the characteristic features or all the pattern remains. So it's like taking a fingerprint and moving it somewhere else. So if you can recognize the fingerprint and shift it back, then you can identify which elements emitted this kind of light. For example, the hydrogen will have some particular lines in the ultraviolet. 1216 angstroms is one of those wavelengths, and if it gets shifted out to some other wavelength. So you need to recognize these things. That's how you know that the atom of this kind exists at that place.
Sure, sure. Thank you. So my next question is about the oldest galaxy that JWST has detected observationally. Somebody is asking what exactly can we see and what are some of the upcoming research outputs that we can anticipate from the JWST about the galaxies, oldest galaxies.
Well, should I answer this?
Anyone.
Okay.
Yeah, Kandu, go ahead. Yeah.
No, I just wanted to say, sorry, Dipankar, maybe, yeah. I just wanted to say the following thing. More than exactly learning about what is the oldest galaxy, just the fact of counting the number of galaxies at various brightness, at various distances away from us, can give a lot of information. Because the way the galaxies are supposed to form is that there are small fluctuations in the density which gravitationally attract and collapse to form these galaxies. And these fluctuations are very small at the epoch where you see the cosmic microwave background. And the characteristic amount of fluctuations depend on all kinds of properties. So you predict what kind of redshift you will form, let's say the first big galaxy. If you see some galaxy beyond that redshift, your theory could be in trouble. So these are the kind of things which astronomers hope to see. They don't want to see anything which you understand. They want to always see something which you can't understand. And that will really make us all excited. So one simple thing is how big is the redshift of the galaxy that you see. Of course, having seen the galaxy, you can look at its whole spectrum in various ways. You can see what kind of stars would have emitted it, whether there are massive stars, whether there are low mass stars, and how old is the stellar population, various other interesting questions. But I just wanted to say, just seeing a very old galaxy at very far away, very young universe would be exciting. Sorry, Dipankar, you can elaborate.
I think you have covered. I don't think I have anything more to add. Yeah, very good. Yes.
Dipankar, there is another question. Maybe somebody is asking what will happen when this telescope will be out of fuel. Certainly, it's there for next 15 to 20 years, but maybe what's going to happen after that?
So to answer that, we have to first understand why does the telescope need fuel at all, right? It does not require fuel for operations like pointing from one direction to another, or capturing images, or sending the message back to us, sending all the data back to us. That doesn't require fuel. It's all being done by solar power. But the fuel is required to maintain its orbit. So it is orbiting around the sun, but trailing the Earth. So it's sitting at some point on the Lagrange point. And the orbits there are not exactly stable for over a long time. So every once in a while, you have to make some little correction. Otherwise, it will drift away. And so the fuel in the Webb is primarily used for that. And the other reason is that because of the bombardment by solar radiation, it gets a little bit of a rotational movement. And to correct that, sometimes the fuel has to be used. So basically, to keep it where it is supposed to be, in an orientation it is supposed to be, you need some fuel. And that control will be lost if fuel is exhausted. And currently, the existing amount of fuel, how long will it last at the existing burn rate? It will last for at least 40 years. So after maybe 40 to 50 years, the drift will become unmanageable. But whether the telescope will actually operate for that long, that's anybody's guess.
Dipankar, if I may add,
Yeah.
So the nominal lifetime is of course 5.5 years, and then it could work for 10 years. But that's not nothing to do with the fuel. As Dipankar said, fuel can make it last for 40 years. But what is critical is the longer wavelength instrument MIRI. It has to operate at 7 Kelvin, and that is achieved through something called cryocoolers. It's not filled helium or anything. It's cryocooler, closed thing. It will last forever, but wear and tear will make it, it can. So the assurance is 10 years. But once that doesn't work, see, other three instruments are passively cooled, and they operate at about 37 Kelvin or so, which the sun shield can block the light, and they can operate that temperature. But the longer wavelength instrument, that is going to be critical, how long the cryocooler will last.
Yeah, so thanks for adding that, Manoj. It is not exactly fuel, but it is a consumable. And it's not a consumable in the sense that it is actually actively being consumed, but because there could be leaks over time, so it could still degrade. And certainly at more than 10 years, it is expected to last. Yeah. For that particular instrument alone. There will be other instruments which will continue to operate.
Sure. Thank you. Another interesting question. I'm not sure if we touched upon this during the discussion or not. Somebody is asking, why is JWST's mirror made of beryllium?
Yeah. So the JWST's mirror is made of beryllium because A, you want something that is light. B, something that conducts heat very easily, and C, something that could be made deformable. So metal mirrors are the way to go. And among metals, beryllium is one of the lightest. So basically, that's the main reason.
Sure, thank you.
Also, if I may, so it was also coated with gold, and it is because gold is an excellent reflector of infrared light. So beryllium mirror coated with gold.
Sure, thank you. This question is a little diverged from the topic that we were discussing, but if any one of you would like to answer, how do you measure the weight and mass or mass of a planet?
I can take it if you want.
Yes, please go ahead.
So among several different detection techniques, one of the earliest, the first planet around a sun-like star was discovered using a technique called radial velocity technique. So this technique actually measures the jitter of the star produced by the planet around it, because of the gravitational pull. See, the planet is going around the star, but actually in reality, it's both star and the planet are moving around the center of mass. Of course, the center of mass is much closer to the star, but still the star is going around. It's so when it is coming to when it goes around, at some point it's coming towards you, then it's moving away from you. So the lines that Kandu explained a while ago, the lines of hydrogen or of various atoms, hydrogen or helium or whatever, they will shift. It will go blue shifted and red shifted. And from the extent of that shift, we can connect that to the mass of the planet, because it's the mass of the it's a gravitational pull of the planet on the star which is causing this movement of the star. So from that you can measure the mass of the planet. It will be uncertain to the extent of the inclination of your orbital plane. If your orbital plane is perfectly, along your line of sight, the rotation axis and the line of sight, the angle is 90 degrees, then if it is perfectly aligned, then you can get the exact mass. But if it is inclined in any other angle, then your mass is uncertain to that. So you'll always measure a minimum mass.
Thank you. This question is about the Stephens quintet. So someone is asking, when two or more galaxies interact, as in the Stephens quintet, how does the fabric of space-time change around it? Professor Subramanian, if you can.
Okay, this is interesting. It does, of course, change. I mean, more dramatic change, I think Dipankar could explain, is when two neutron stars will merge to form a black hole. Then, of course, you can get gravitational waves and all that. Of course, it does change, but the gravitational field of a galaxy is not strong enough for you to really do dramatic changes to the fabric of space-time or changes in terms of emission of gravitational waves, etc. The kind of measure of that would be to take the velocity of the stars in the galaxy and divide it by the speed of light. And stars in the galaxy would go, let's say, at a few hundred kilometers per second. The speed of light is 300,000 kilometers per second. So roughly, this ratio is pretty small compared to 1. For a black hole, it's of order 1 when things are going around in black hole. So mergers of black hole, of course, will change lots of interesting things in the fabric of space-time. Everything will change in the fabric of space-time, and the effect will be small and imperceptible by most observation.
Sure. Thank you. We have a lot more questions coming in, but in the interest of time, we'll have to bring this to an end. So these first images from the James Webb Space Telescope are really jaw-dropping, and we'll request you to take a moment to zoom into each of these images and go through the details that we have discussed in today's discussion. The sheer amount of information that each of these images contain is dizzying, but the treasure trove comes only from only a few days of observation, and so far the telescope has only looked at just a minute fraction of the sky. So Webb will be capturing the cosmos for, like we discussed, for the next 20 years. So there's a checklist of discoveries that astronomers, astrophysicists across the globe are hoping to tick off, from seeing the first stars to shine to finding habitable planets beyond our solar system. But the thing that's most exciting to scientists is the discoveries that haven't even they have dreamt of so far. So I hope you have enjoyed the session as much as I did. I would like to extend a big thank you to all the panelists and to all the audience members who spared their time and joined us for this discussion. we would request you to take a couple of minutes to share your feedback. The link has been shared in the chat box. The next session on that note, I would like to highlight is on biology and will be delivered by Dr. Lasya Samita, who is a biologist. So doing science, she says, is often viewed as a reclusive enterprise, and it conjures up the picture of wild-eyed genius working in a stuffy lab day and night. In this talk, Lasya aims to bust these myths and some other using real-world examples. She will be discussing the work done by renowned Indian women scientists, Dr. Priyambada Mohantani Hijmadi, who studied how lost body parts can be regrown in some organisms. Just like how in the Harry Potter series, using the transfiguration spells, we used to see that one object used to get converted into another. Similarly, something wrong that gets grown in one part of the body can be replaced by something else. For example, when the tail is cut off, a leg is grown in that region. So in the upcoming session, we will be discussing the history and biological principles behind such dramatic biological transformations. The session is scheduled on 23rd of September from 6 to 7 p.m. IST. I would like to also inform our audience that the registrations for the undergraduate program will be starting next year. If we can go to the next slide, thank you. That is August 2023 are now open. I would encourage students to start early and have access to the personalized mentorship with our academic counselors, interactions with Ashoka students to learn more about the campus life and receive guidance for Ashoka's holistic admission process. On that note, I would like to again extend a big thank you to Professor Subramanian, Professor Manoj, Professor Dipankar, Professor Jesse, and to all the organizing members. I would also like to extend a big thank you to Philip, a PhD student in the physics department who helped me curate this discussion. So please take care of yourself, stay safe, and thank you for joining once again.
Thank you.
Thank you.
Thank you. Thank you.
Thank you very much.
Thank you. Thank you.
Thank you.
Yeah.